Yeah.
Okay, yeah, welcome. Thanks. We've got a really pleased to actually present Richard. So thanks again for doing a great contribution over the years to continue to. So thanks a lot, Richard. So talk us on sleep. So
Yep.
Thanks very much.
Okay, Chris, thank you. Right, so nothing really technical about today's talk. It's just general interest stuff, but it's something we can all relate to. I've chosen this topic for sort of two reasons. First of all, my passion is on the brain, and within the brain, one of the passions is to do with sleep, various aspects of that, and so we'll be touching on some of those. I lead the Christchurch Neurotechnology Research Program, and I just thought most of you will know what that's all about, but for those who don't, so it's based at the Brain Research Institute, and it's a close collaboration between University of Canterbury, hi Steve, with electrical and psychology, the University of Otago, Department of Medicine, the District Health Board, because we've got the sleep unit there, and Medical Physics Department, and the Brain Research Institute itself. And the focus of the Neurotech is on sleep. So, and the big area that we work on is this thing called microsleeps, and that's the one area that we're not going to talk about today. We are going to talk about the next one, which is to do with obstructive sleep apnea. And another one I'm going to just talk briefly about is this concept called local sleeps, which we're not starting up, but we want to do, so, and you'll see why later on. So, here are the topics I'm going to talk about. There are three of them. So one's to do with sleep apnea. The second one is why do we need to sleep at all, which is actually quite an interesting question, not as obvious as you might think. And this other thing about local sleeps. So, why is sleep apnea bad for your brain? So first of all, what is obstructive sleep apnea? So basically this is where when you're sleeping at night and your pharynx and your upper airway sort of closes during the night, and you just stop breathing. And you stop breathing for 10 seconds or more, that's called an apnea. And if you sort of does a partial blockage, it's called a hypopnea. So when these things happen, what happens is that you get an oxygen desaturation occurring in the brain, and that's a problem. You also, because of that, you get these frequent arousals from your sleep. So you're in deep sleep and you get this, you stop breathing and this wakes you up, which even if you're not aware of it. So that's not so good either. And so you get very fragmented sleep as well. So the severity of sleep apnea is termed in terms of this thing called an AHI index, which is the number of apneas or hypopneas you have per hour. So if you go into the sleep unit, they'll do the tests on you, and you'll come out with one of these sort of categories. So mild is where you have somewhere between 5 and 14 of these apneas or hypopneas. Moderate is 15 to 29, and if you're getting over 30 or so, that's called severe. And there's certainly been cases that they've seen at the sleep unit at Christchurch Hospital, they're up in the order of 200. You know, this is per hour, so it's quite a few.
Can you actually suffocate?
Pardon?
Are there cases where people literally suffocate?
That's a good question. I don't know. I mean, I don't know. Is it the equivalent of cot death, for example? I'm not aware of that. Usually it gets into the point where the CO2 levels are such that it sort of wakes you up. But yeah, I'll have to check on that one. That's a good one. So there's lots of studies been done on sleep apnea, and they've sort of shown that it causes all sorts of problems with your health. So you end up with hypertension, cardiovascular disease, stroke, diabetes, cognitive dysfunction. And also, because of this waking up thing, you get this excessive daytime sleepiness, which is a big problem a lot of people with sleep apnea have. And so if you have that, you get this increased risk of these microsleeps thing. And if you're getting microsleeps during the day, when you're driving, for example, that's when you might well have a fatal accident. So we, a few years ago back wanted to ask the question, does sleep apnea affect the brain when you're awake. And so we did this study where we got 19 participants who did have sleep apnea. Some were at 11 mild, 4 moderate and 4 severe. And because these numbers were relatively low, we actually grouped them together, so moderate, severe with an 8. And 19 controls, so we could do the comparison. They all did a level 2 sleep study, as it's called, at home, where they get this 34 channels of polysomnography. So they go into the hospital, into the sleep unit, and they all get rigged up, and then they have to sort of quietly get out of the hospital with all this bloody electrodes all over their head, and they're going to measure all things to do with breathing. You've got looking at EMG as well, so it's all sorts of things. But the idea of this is to confirm that they do have sleep apnea, or to confirm that they don't have it, and also to see what level of sleep apnea they have. And we in fact had quite a few of the controls that we got in. We found that in fact they were ending up with going into the other category. They had sleep apnea and they weren't aware of it. And it hadn't been brought to their attention by their partner, for example, just hearing them stopping breathing during the night. And certainly one of the subjects, the controls, he was in the severe sleep apnea case. But he also wasn't drowsy during the day. So there are different phenotypes, as they are called, of sleep apnea, which affect things in different ways. Anyway, so we got all these subjects and we put them through some MRI scanning, and we were looking at two types of thing. One was the structural side, so we're doing this thing called voxel-based morphometry, and this is really looking at the concentration of grey matter in the brain. And the other thing we were looking at was called the more functional side of things, which is arterial spin labelling, which allows us to give us an absolute measure of their perfusion throughout the brain. Quite a tricky technique. It's relatively recent that it's come in as a tool. This is the essence of how it is, how it's done. So what happens is that your arterial blood is coming up from the heart, coming up here in those arteries, carotid artery, for example, and the scanner magnetically tags the blood, tags it here, and it all goes up here, and then you do multiple slices here. But during one slice, the MRI scanner is looking to see how much is the blood is being tagged. Very tricky. Subtracts a control image, and basically it does an average over 5 minutes. So you're at rest, not doing anything, and it's just measuring your at-rest perfusion throughout the brain. And it is throughout the brain with these at that sort of level, 5 millimetres by 2 by 2. But basically, at each of those voxels, it's saying how much blood was delivered to that voxel over the 5 minutes. And what did we find? So we found that, in fact, on the structural side, with the group that we had, that there were no differences in grey matter. So there's no structural problems showing, at least at that stage. And on the cerebral perfusion side, we found that there was no difference between those who had mild sleep apnea and the controls. But if we took the other group, which is the moderate severe group, in fact, that we found that they had reduced perfusion in several areas, and 3 clusters, in fact, in the brain when they are awake. So this is what it looks like. We don't need to know what the details are, but these blue regions here are areas in the brain where the amount of perfusion during the day when you're awake is actually down. So something's happened, and it's due to the sleep apnea that's caused this. So those are showing that these are significantly down, but then how much are they down, in a sense? And so this is where we're looking at this here. So if we look at this graph here, we have, this is cerebral perfusion up the vertical axis, and here we have the controls. Here's the mild sleep apnea, and here's the moderate severe group. And you can see that there's quite a bit of overlap between those groups in terms of their perfusion, but you can see a definite downward trend. So on the main thing was that the control group had a perfusion of 70, the milds had 63, and the moderate severe were 55. So the moderate severe group, they were 21% down on their, in terms of the amount of blood that was sort of feeding into each of those voxels in those blue regions. So it's quite a big drop.
Richard, that bottom outlier in the control group, that wouldn't tend to be that severe person that was bound to be in severe.
Well, offhand, I don't know. That's a fair question.
You would have changed though. The person who was originally in the control group would have
Yes,
changed.
that is true. So, okay, that's a good point. So that person was definitely not left in the control group because they were categorised as one of the severes. No, good point, Phil. So basically what we concluded from this study was that this chronic intermittent hypoxia in the brain, which is occurring over every night, lots of times, and can be in many cases over several years, is actually stuffing up the regulatory, the circulation regulation in the brain. Exactly how it's doing that we don't know, but that's where those blue regions are coming from.
Is it likely to be significant that they're both on the left, or the two of those regions are on the left? One was central and looked like two were on the left.
Let's go back. Well, you know, those are on different sides.
Oh,
this is central. That's the big one, which is sort of in the cingulate gyrus is the big one, and the right one here is an important one. That's the thalamus, which is a big.
Actually, I see what you mean. There's really two, right?
Yeah, it's what, and you know, it's all a matter of statistics as well in terms of where it shows up. So. Now, the other thing is that although we observed no structural changes, the fact is that other studies, which have used more severe subjects, have shown that there is structural damage in certain areas of the brain, which coincides with the areas that we found were blue as well. So as a result of that, we sort of hypothesise that cerebral perfusion changes occur before, at an earlier stage, before the structural damage is actually done. And basically that if you can detect this at an early stage and you can reverse the sleep apnea, then you can prevent the structural damage, which is irreversible, actually happening. So now I want to sort of keep on the sleep apnea thing, but I want to show that there's a link between sleep and sleep apnea and Alzheimer's disease, which is actually quite intriguing, if a bit concerning. And so what is Alzheimer's disease? So basically, it's where you get these aggregates of these toxic metabolite proteins. They're generated in our brain, in all of us. So they're generated, but it's just a normal process, but they're being cleared as well. So the famous one is this beta amyloid one, which has been found in a lot of cases with people with Alzheimer's. And there's another one related to it called these phosphorylated tau tangles. Anyway, they're all hallmarks of Alzheimer's disease. And so what happens is you get down the bottom here, you're getting these little dots here are these amyloid things, and they start clumping together, and eventually, you know, we're talking, this can be years, it can cause problems and actually can, so it can actually start causing damage to the neurons and in terms of neural function, etc. So this abnormal accumulation is because of an imbalance between the production of these metabolites and also in the clearance. And the clearance mechanisms, which there are several in the brain, to get rid of them, as it occurs basically at night. So this is what happens. So during wakefulness, the extracellular levels of those toxic metabolites that we've been talking about, the beta amyloid, etc., so they increase. This is what's happened. The red one here is the increase. So this is increasing here. This is wake, sleep, wake. The black line is showing basically our sleep drive, which increases during the day and then it gets settled when we're sleeping. But this is we can also see how the amyloid, these metabolite concentrations increase during the day when we're awake, and what happens, and overnight they then cut down. There's a delay here, as you see, there's a 6-hour gap, as it's called, because this is being picked up at the spinal cord level in the lumbar space. So there's a bit of a delay there, but basically you can see that the clearance of these metabolites happens at night when you're sleeping. So the bottom line of that is that if you get insufficient sleep or it's disrupted sleep by whatever mechanism, that gives reduced clearance. And if you get reduced clearance, ultimately you'll have problems with collections of these metabolites. And if you're unlucky, you'll end up with Alzheimer's disease. Now this was this interesting study that just came out earlier this year, and this was just taking normal people, and it was sleep depriving them just for one night, and it was showing that what happens, that they were able to show that just one night's sleep deprivation, perhaps it's easiest to see it on this graph here. This was when they were seen in the scanner, in a PET scanner, which was labelling these amyloid things, and when they were rested, this was the levels of the amyloid, but after one night's sleep deprivation, you'll see that these levels have gone up. So even just one single night, they were able to detect that these amyloid levels had actually raised, and of course it's sleep that actually reduces them again. And then these are two important regions well, hippocampus is one of the regions that it showed. Hippocampus is, of course, to do with memory processes, and the thalamus is involved in lots of things. So quite an interesting study to be able to demonstrate that after just one night in normal healthy people. So, and then there's another thing. So with the sleep apnea, you get this disrupted sleep, and we said that causes problems. But the other thing is that they've shown in animal studies that this repeated hypoxia in the brain actually increases levels of this amyloid. It hasn't been shown directly in the brain in humans, but it's just showing that the sleep apnea is an important part of that process, because it's characterised by this intermittent hypoxia during the night. And there has actually been another study which has shown in humans, just looking at the amount of amyloid and tau just in the blood, that these levels are higher in people who have sleep apnea, and that these levels of those metabolites is correlated with the sleep apnea severity, which is the AHI index, and the other thing you can do is the level of oxygen desaturation they get. So this indicates that chronic intermittent hypoxia, as happens during sleep apnea, contributes to this pathogenesis over a longer period to Alzheimer's disease. So from this we can conclude that basically that sleep apnea causes a risk of developing Alzheimer's disease, or increases the rate of progression of it, and it does it by two potential mechanisms. One is to do with this poor fragmented sleep, and the other one is by this hypoxia that's occurring multiple times during the night. But to be fair, the exact mechanisms as to how this all sort of works is not clear. So what do we do about it? Most of you will have heard of the treatment with sleep apnea is called CPAP, which is continuous positive airway pressure. So basically, it's quite a simple mechanism in principle, is that you have to put this mask on here, and basically it increases the pressure in your airways and blows them apart a bit so that it doesn't collapse completely and stop your breathing. So this is some of the devices that are used, and that this sleep unit sort of prescribes quite a few of these. But the thing about it is that in New Zealand they're only available to be publicly funded for those who have been labelled as with severe sleep apnea. it's not, I mean, it's not everyone's sort of cup of tea, not surprisingly. It's not particularly sociable in a sense, whatever, but some people can't stand it, and other people just swear by it. It's just made such a big difference to their lives. That's CPAP. So we wondered whether, in fact, CPAP would actually be of value for those who have moderate sleep apnea, so who are not actually at the moment eligible for funded CPAP. So we have, we're in the sort of middle towards getting past the middle point to do with a big study based in the sleep unit, where we're looking at people who have moderate sleep apnea, and we're wanting to look at the cerebral perfusion that we were looking at before, looking at measuring their cognition, looking at the propensity they have for having these microsleeps that I mentioned, and we also want to show, it's a longitudinal study, so that we want to show that there's some benefit of CPAP even over a period of 6 months. Whether it does or not, well, we're still at that phase, so we don't know. So this is basically the method that we're using. So we've got 30 referrals to the sleep unit who have been confirmed to have moderate sleep apnea, and 15 of them go into the treatment arm with CPAP, and 15 of them have agreed to go for 6 months without the treatment. I mean, they wouldn't get it anyway, so, but unless they paid for it, that is. And so the treatment, as we said, is 6 months of CPAP. We do 2 assessments, one at baseline, so we want to show whether, in fact, the moderate sleep apneas do, in fact, have decreased perfusion, decreased cognition, increased microsleep propensity at baseline, and then we want to see what happens over that 6 months. And if all goes well, and we demonstrate substantial differences, well, then we might have to approach the government to see if we can get funding for moderate sleep apnea cases. Right, so we move on to topic number 2, which is, why do we sleep? So, first a wee bit about sleep in general, just to give you a feel for things. So, as you probably know, all animals sleep. So any animal that has a brain has to sleep, unless it was a hardwired brain. If it was a completely hardwired brain, they wouldn't need to sleep. So there's a clue in that. But there are, interestingly enough, there are some animals and some birds who actually sleep with only one side of the brain at a time. And dolphins are known to do that, and some of the migratory birds do the same. So that's how they can keep going for such long periods. They sleep on the right-hand side, the other bit's awake, and then swap around. But just demonstrating that they've got to sleep.
Why are you looking at me?
So clearly sleep fulfills a fundamental need in the brain, but which is not needed for the rest of the body. We only go to sleep because of the brain. So it's an essential function, and for some reason or other, evolution wasn't able to fix things so you didn't need to sleep. But what does this need? So before we sort of get into that, I'll just talk a wee bit more about what happens when we sleep. So some basic facts. So there are various stages. There's 3 stages of what's called non-REM sleep. So stage 1 is where we're sort of going through that sort of transition phase. We're not asleep, but we're not awake. You've got to go through that. Then we go into light sleep, and then we go into deep sleep, which is also called slow wave sleep, because you'll see shortly, the EEG, if you look at it, has lots of these slow waves. And the other type is REM sleep, which is rapid eye movement, which is when you do the bulk of your dreaming, and probably some other things as well. This is what happened. If you recorded during the night, an overnight session, you're shown this generates a thing called a hypnogram, and we go through these sleep cycles of about 90 minutes. So we have several of these per night. So what happens, we're starting off here, we start awake, go straight down into stage 1 non-REM, stage 2, stage 3. So that's the deep sleep. That is the deepest sleep that there is. Then we come out of it again, we go to REM sleep for a bit, then we go down into another. Now the other thing, you'll notice is that in these cycles, what is changing is that there's a lot of deep sleep initially, but as you go through the night, in fact, there's not much deep sleep at all. And if you do get to the point of 5 cycles, you won't have any deep sleep at all, but you'll have more REM sleep. And these little things here are called arousals. So these are just normal things. This is not to do with sleep apnea or anything like that. And so you really are going to the awake stage, even if you're not awake. You're sort of aware that you're awake. So that's the hypnogram. And so we have 2 things which are sort of driving our sleep. One is this homeostatic, the main one is this homeostatic pressure to sleep. In other words, the more that we are awake, the more the brain wants to sleep. So that's the sleep pressure here. So here we wake up at 7 a.m, say, and the pressure to sleep increases during the day, and then you go to sleep, and then it drops off again. So there's homeostatic pressure, and there's this other thing called circadian rhythms, for which there are 2 sort of peaks. The big peak is sort of like between sort of 3 and 4 a.m. in the morning, but there's another one which is around about now, which is just a coincidence, by the way. And so, and particularly after lunch or anything like that. So that's the other circadian rhythm. In terms of so normal sleepers, it's 7 hours or so. Long sleepers 9 hours. Short sleepers 5 hours or so. And some people really can and are known to just quite well and function well on 3 hours per night. Apparently most people can adapt with the pressure to between 4.5 to 5 hours of sleep and function pretty well. And so some ultra short sleepers, as I say, can get down to the order of 3 hours. Apparently Margaret Thatcher was one of these, but there'll be a few of those sorts of people.
Richard,
This
sorry.
is not your recommendation, is it?
Yes. Sorry, Richard, the times are obviously flexible, so you can move this. I mean, we're not tied to 7 o'clock.
Oh, no, not at all, no.
But do people that work shifts, for example,
It's a major
does
problem.
it change?
Of course, it's a major problem, yes. So,
Because you're trying to do sunlight.
yes,
cycle as
it's
well.
related to that, but it's just, yes, so they have, needless to say, shift work is a major problem with people in terms of sleep, going to sleep on the job and all that sort of thing. Yeah. But eventually you do change. So apparently much of the stage 2 sleep seems optional. You can sort of do without much of it. REM sleep seems involved in the consolidation of memories, but there's not too much known about what that's about. Most dreaming occurs during REM sleep, but it also occurs during the deep sleep. And apparently the longest study on sleep deprivation that's been seen was by the 17-year-old who was able to either keep himself awake or was kept awake, I'm not sure exactly what, for 11 days. But the interesting thing was, even though which is quite a long time, but he was able to get get back to where he was after just one long night of sleep. So he didn't need to have sort of like another 11 days of long sleeps to get back there again. So the brain really does have a whole lot of complex pathways and neurotransmitters and systems for controlling this wake-sleep thing. That's pretty important. So what are the functions of sleep? And we're sort of building up to the crunch one. So we talked about the clearance of those toxic metabolites before. So that happens when you're asleep. there's this memory consolidation and forgetting seems to happen when you're asleep. There are studies that have shown that. There's a sort of somewhat ill-defined neuronal recovery and neocortical maintenance, those sorts of general sorts of terms, but they're fairly fuzzy. There's a few other things that have been sort of put forward as well. But I always thought for many years that there was just in all this story that there was something sort of missing. And it's sort of typified by, there were two books. First of all, there's a book that came out in 1988 called Why We Sleep. And at the end of that book, you didn't have a feel for why you sleep. And there's another book that came out last year, and unbelievably, it's the same thing. It didn't actually explain. It said things that, talks about sleep disorders and what you do, processes, etc., but it didn't actually get to the why we need to sleep. And I went to two world congresses on sleep some years ago, and while again it was covering all sorts of things, it again didn't cover that basic question, why do you sleep? And why has evolution left us with this need for sleep, when obviously there are distinct advantages of not going to sleep, because it's a bit of a dangerous thing, when you're sleeping. Make yourself vulnerable.
Do any creatures not sleep?
No. Anyone?
At any level? Bacteria?
They have to have a
brain.
Yeah, they have to have a brain.
Yeah, right.
Yeah, so the brain's the critical bit of it, and not
But there's not been an alternative brain.
Yes, and I don't know if there are any creatures even in that category. There probably are, but I don't know. But it's to do with it is to do with plasticity anyway. This is where this is all going.
Yeah, Phil, sleeps.
Yep. Oh, yeah.
Sort of distributed brain.
Yeah, but even a distributed brain is fine, as long as they've got a brain. Yeah. So, and then I came up with this sort of belated recognition that the primary role of sleep, and it wasn't me who came up with this, is to do with plasticity, as we were just talking about, and also to do with synapses. So this is the key to why we need to sleep. And it really came out of what's called a synaptic homeostasis hypothesis, which is from the University of Wisconsin Sleep and Consciousness Center. And they came up with this proposal, this hypothesis, that during wakefulness, the learning processes basically increase the weights of the synaptic strengths in our brain. They're going up all the time as we're learning things, doing things. And at night, we get this downscaling. Okay, so you can only go so far before you get into the sleep deprivation mode, and you can't learn any more. So that's what happens in wakefulness, and during sleep, you get this downscaling thing. And also, that's where the memory thing kicks in. So the goal of sleep, the bottom line is that it's the homeostatic regulation of this total synaptic strength throughout the brain. And it's actually this hypothesis, although it's fairly difficult to prove per se, there are lots of experimental studies which have indicated which seriously support it. And so Tononi came up with this sort of quote at the bottom here, which is pretty neat actually, that sleep is the price we have to pay for plasticity. So if we want plasticity, which means the ability to learn, we have to sleep because of this upscaling and downscaling thing. So here's there's a two-process model of sleep regulation, as it's called, but what's important, and we were talking about the circadian and the homeostatic component. This is the homeostatic. This is when they're awake. So during the day, as we showed before, this is the build up and your strength, the want to sleep, but it's also, this is the weight of the hypothetical weight of all the synaptic weights in the brain. So these build up, and they get sort of a bit saturated, and then at night when we sleep, you get the synaptic downscaling. So it just comes down to that. And to sort of give you a bit of an example of it without going into the fine details of it, so this over here is, on the left-hand side, is when we are awake, and so we're in our learning phase. So let's say we start off the day down here, we've got a dendrite there, and we've got these synapses here with their different weights. And at the end of the day, after we've done some learning, we end up with the top one hasn't changed. That wasn't related to anything to do with learning, whereas the middle one was involved in learning, and so its weight's gone up from 100 to 150. And also, we now have a new synapse starting at the bottom. So that's all part of this learning process. And then we go into sleep, and we have this slow wave increase that happens in the synaptic downscaling. And so what happens over the night is that the top one, all of these are going to be downscaled. So the top one goes from 100 down to 80. This one here goes from 150 to 120, still going down. And the bottom one, if it was only there, it was only a small connection, as such it just gets chopped off, pruned is the term. So that's why we sleep. So, moving on to the third and final topic, this is called local sleeps. So what are local sleeps? And this came to my attention. It was actually by quite an amazing study, actually, I think, that by the same group that we were talking about before, this University of Wisconsin, and they put a paper out in Nature in 2011, and it was talking about local sleep in awake rats. Basically what they did was, so in these rats, they were able to implant all sorts of these wire electrodes and really get down to the neuronal level to look at what was happening, and they sleep deprived them. And they found that they were having these local sleeps, which I'll show you in a moment what was happening. So basically small bits of the brain were going offline, they were just stopping, which is what happens when we're in our deep sleep, when we are asleep. So it's a similar sort of phenomenon, but it's happening when you're awake. It hasn't been observed directly in humans, and it's something that we're actually quite keen to do, and we think we've got signal processing tools that might be able to do this just from the scalp EEG. We'll wait and see on that. So the bit in green at the bottom is the key to this. So we have, we're in the stage 2 part of a Marsden, which we really hope to get, of course, and the idea is to show that two things really. We want to be able to show that these local sleeps do occur in humans, and they nearly definitely do, but we want to show it, and we also want to show that these local sleeps, when they happen, actually cause certain errors in our performance, whether it's cognition or sensory motor function or whatever. So this is what we've got to do, that correlation thing. So this is from the rat study, and so this shows you how these local sleeps happen. So this is down at the neuronal level. So this is recording individual neurons firing away when the rats are awake, and you see that just keeps going. That's fine, and this is this is the EEG on the scalp at the top. When they are asleep, so we're now in the rats are now allowed to go to sleep, deep sleep. We see the same sort of thing here, but you'll notice how there's these big gaps happening. The gaps here, so they're just stopping, the neurons are stopped firing, so they're sort of, as I say, gone offline a bit. And when that happens, what you see are these big waves occurring on the scalp. So these are the slow waves that we're talking about, and those are the slow waves that we have when we are observed when we're sleeping in the stage 2 sleep. This is awake, this is when they're deep sleep, and this is when they're awake but sleep deprived. And what was happening was that they were coming along here, and they were also having these gaps where things were stopping. And that there is what they're calling a local sleep. So the brain is getting tired, really tired, it wants to go to sleep, but it's not quite got to the actually going to sleep yet. And so, but it just stops in certain bits, just little small areas of the brain, which will be flicking around all over the place, and you get those just single slow waves. So, so basically that's it. It would be great if we got the funding to really look further at this thing. And so, does this explain everything to do with sleep? And of course it doesn't. So it doesn't. There are lots of questions remaining. You know, why do we have these cycles of sleep? These 90-minute cycles when we're asleep. What's the role of the various stages? What's the role of the REM sleep? Role of dreaming? How does this memory consolidation thing happen during the night to do with synaptic downscaling? Can one have local sleeps when awake, which is the thing which I'm sure we do and that we want to look at. And another intriguing side of it is, can we have local wakes when we are asleep? So, and there's evidence of that as well. I mean, things like, you know, sleepwalking and sleep talking, etc. You are sort of awake, but you're sort of asleep too. So it's quite intriguing. So, final slide. So the take-home messages from all of this is that clearly sleep is an essential process, an essential need in all animals, and it's the price that we need to pay for plasticity, our ability to learn. In terms of obstructive sleep apnea, it causes lots of problems in the health side of things, including the brain. CPAP is the treatment of choice and basically, so if you or your partner are concerned about the possibility that you've got sleep apnea, you should consider getting a referral to the sleep unit and for a proper assessment for the possibility of getting CPAP, although there are some alternative treatments as well. That's it.
Cool. So this biological need for sleep, I'm gathering it's due to some fairly fundamental biological restraints or constraints within the brain.
Yep.
And the way it's set up. So could it be chemically altered? So you could chemically or artificially speed up the process
of
the resetting, the reweighting.
Yes, that's a fair question. There are sort of studies that have been looking into whether playing certain music when you're asleep or whatever, whether that changes your sleep stages so that you get more stage 3 sleep, which is the most critical one. And so if you've got problems with insomnia, you know, things they're looking at means of treating so you get you to sleep without having to use sleeping tablets all the time. Whether so that process can be altered, but the basic process can't be. You have to have it for the reason I explained.
I wonder if dreaming's a little bit like simulated annealing, you know, during the settling down.
Yeah.
We're sort of jiggling things a bit to make sure we don't settle into a local minimum. We're sort of allowing it to stretch because, you know, dreams seem to be like extensions of our existing memory, don't they?
Well,
you
they
take
sort of,
things and people and you juxtapose them and mess them around.
Well, they sort of are, but they get pretty messed.
Yeah.
I mean, you know, there's a lot of dreams. Where the hell did that come from?
Well, of course.
Sort of thing. So,
yeah.
But yeah, I know. And you know, is that to do with the consolidation? So really, we don't know why we dream. But it's something to do with that learning consolidation process.
In dreaming, I've heard that you can control your dreams, so that you actually dream, that you can control what you talk. Is there any evidence that people are awake or are they still asleep, or can you see a difference by people doing that instead of people just dreaming normally?
Wow. No, I really don't know. I didn't know you could control dream.
I've heard about it.
I've done that. You say, "Oh, wake up now," or start flying.
Yeah, you can train.
We're gonna fight. Say, "Oh, we're
What do you
gonna
think
fight."
about before you fall?
Somehow you remember to think about how you're going to dream, and then if you realise you're going to dream and don't wake up,
Yeah.
you can start thinking about other things that shape your dream.
Or like shearing dreams, shear dreams.
Don't know about that.
As in like lead shows, like the movie. Yeah.
Oh,
I think you might need some physical information to make that happen.
What about what was saying about self-induced, so trance state, for example, or hypnosis?
and even meditation.
And where it, yes, and where it actually fits on that scale.
Yeah.
Seen any of that?
That's a good question. I don't know the answer to that. Yeah.
Richard, for you,
Okay.
for this OSH study that you did, I noticed that they were all older. Is it an age-related thing? So your patient started at 41?
Yeah, it
Sort of a muscle relaxation.
it certainly is age related.
Yeah.
And obviously it's related to, I think like obesity, that's obese, you have more problems with the sort of floppy throat and it's more likely to close, all that sort of thing. So it seems to be due to the sort of basic muscular weakening or whatever.
I just turned 41, I noticed.
Yeah.
Meet the bottom end there.
Is CPAP a cure, or is it just a treatment? It's never actually you relying on it.
Yeah, you need to.
There's never any cases where you might actually.
No, it's not a cure. It's purely symptomatic.
There's no cure.
There can be a cure for some people. Where it's appropriate, they can get some surgery.
Oh,
And I know people have had the surgery, so they can do certain things to cut things out, and because that's where the blockage is. And that really that is a cure.
Presumably losing weight for it.
Yeah, that's another thing too. Yeah, so there's strengthening. So apparently one of the pharynx, which is the thing in here, which is where it that's the thing that closes in. One of the main muscles that actually it's called the genioglossus muscle, which is the one that sort of closes it and opens it, and that muscle also is related to poking out your tongue, believe it or not. So it was actually put forward as a possible treatment. Yeah, that's exactly that. Yeah. Just to do it quite strengthen the, because seriously, if you can strengthen the muscle, that would help fix it.
So it sounds very similar to when you got short-sighted old age in terms of your muscles.
Yeah, that's a similar thing.
I was wondering about the multi-day not sleeping. So the multi-sport people in this country would be quite interesting to look at. You have a prime case of people not sleeping for 5 days or very little, but being very fit.
Yeah, I don't know how they do it. Yeah.
Regret all those talks now.
Richard, you don't happen to know if there's any research being done in plasticity involved with artificial brains, neural networks, and whether they need some sort of reset timing?
Oh, that's an interesting question too. I imagine not, because you can build some sort of decay into the process, so you don't have to have a night and awake in a sleep state. But
there's no chemical build-up, so that chemical removal is very
well, that's part of it. But the homeostasis thing is not to do with the chemical thing. And I still wonder whether the whole thing about those metabolites being taken out when you're asleep might be just a secondary thing. If you've got to sleep anyway through evolution, so we might as well do as much as we can while you're asleep. And I don't know.
You don't do any of that way.
Yes, Lou.
I'm just following both questions. Like, if the sleep do regulate the plasticity that form the weakness period, which we may be able to observe variation. Or like, suppose you are training to do some tasks. The other day before and after sleep, we should see some variations. secondly, at the same task, performance should change, or I mean, if that's artificial, if we follow the artificial neural networks, if we do regulating the synapses, so the performance should change, like classification performance or the visual model performance that you mentioned. That could change. So, I mean, after they training that for some task for 4 hours, sleep for like a whole day, and the next day we should observe the retraining process, the gradual improvement in performance.
I'm a bit of a skeptic when it comes to artificial neural networks in terms of.
Yeah, I'm just guessing.
No. I mean, I'm not against them by any means. We use them, but just in terms of sort of saying that this the brain is like an artificial neural network is just so far off that, as you know, so the parallel between the two is pretty weak actually.
Matthew has started his own experiment.
That's right.
But I thought, in a sense, you were saying if this is happening in humans, this homeostasis, it'd be interesting to know whether your performance at the end of the day, before the homeostasis, and the following morning is different in some way. It may have actually improved. It may have actually improved because the homeostasis might remove some of those little interfering things.
Well, I think if that's sorry, I might have missed the point.
Yeah.
but I think that's true. When we're late at night, we're still trying to keep awake, still trying to function.
Don't we all have that experience when you're doing something that's unrelated? Suddenly you get the idea.
Yeah, right.
Or something that you've been mulling over for days suddenly becomes clear. It's wonderful when it happens.
Yeah.
It doesn't happen very often to me anymore. But nevertheless, it's usually riding my bike or something. So it's something that's heavy physical. So maybe
there's some kind of a readaptation period for even repeat single task if the plasticity hypothesis is correct. I mean, second thing I would like to, I'm quite interested about is local sleep.
Yeah.
So the Nature paper basically mentioned that local sleep happens just because of the drowsiness or sleep deprivation.
Yes.
I know you are working on microsleeps and mind blank and mind wandering. So I mean, just because they look at the experimental setup and say, okay, the rats are moving freely with the cerebral cortex.
Yeah.
So I'm just wondering because we are only monitoring that particular region. We don't because rats has more control. We are not asking them to perform anything. So basically, we do observe EEG like sleep patterns, but it's not like what you did in your experiment, like zero performance. There's no zero performance in that case. You know what I mean?
Sorry, I missed the key bit of that.
You mean they're not measuring performance?
Yeah, right. There's no measure.
Well, they were measuring performance, and I didn't mention that. But that's a mistake. So those rats were performing a sugar-reaching task. So they were using their paws to get it. And what they found, and I said, that's a key bit. So the rats were doing the task, and when they had these local sleeps, in certain cases, they were malfunctioning with their sugar reaching.
Okay.
So there was a connection there in the rats.
Coffee to create some more sleep deprivation.
Yeah, that's right.
Coffee does it.
But we're talking about whether it happens when you're sleep deprived, and no doubt it's more. But it wouldn't surprise me at all if it basically this process of local sleep is actually happening all the time to some degree now.
Yeah. Just like a couple of weeks ago, I was in a meeting and asked to talk about my work recently, and I'd not had a coffee that morning, and I was just completely mind blank. And then a few minutes later, I was fine.
Yeah, any excuse.
Yeah, that is a different phenomenon.
Is it?
That'll be a different talk, which Claire will be at.
I think I should thank him again.